All right, ladies and gentlemen, we're going to take a look at section 5.2 in this video, dealing with infinite series. And so we have to start by defining what a series is. A series is simply the sum of a sequence. The notation that we use for such a thing, a notation we cover heavily in, say, a pre-calculus class, would be something like this. You use the Greek letter capital sigma with an index n running from 1 to infinity of your terms of the sequence that you can denote as a sub n, and this represents as n is 1, a1, as n is 2, a sub 2, as n is 3, a sub 3, and so on, and so on, and so on. Now, our goal is to understand how to talk about the sum of this infinite set of numbers. And of course, since it's an infinite set of numbers, that poses a challenge to us. And what meets that challenge for us in a calculus context is the concept of the limit. The limit process is what we use to understand what it means to sum an infinite set of numbers. Okay? And the way we're going to carry out this limit process analysis of the sum of an infinite set of numbers is to introduce the idea of what's called a partial sum. So, definition. The partial sum of a series, which we denote S sub k, S for sum, k being how many of the terms we're actually summing in this thing called the partial sum. This is the first k terms summed. So the sum of the first k terms of the series. Okay? And so in notation, using sigma to represent that, in other words, we can say that S sub k is the sum as your index runs from 1 up to k, not to infinity, of the first k terms. Okay? And again, that means that's a1 plus a2 plus a3, on and on, up to the kth term. Okay? Now, when we take the limit of this partial sum as k goes to infinity, as this k goes to infinity, this k goes to infinity, we are then representing the infinite sum of the sequence. Okay? The limit as k goes to infinity of that partial sum is the sum of the infinite series. Okay? If this limit exists, then this sum exists, and we say therefore that the series converges. If this limit does not exist, then this sum doesn't exist, and we say the series diverges. Okay? So if the limit as k goes to infinity of S sub k exists, then the series converges to the value of the limit. If, on the other hand, that limit does not exist, if this limit does not exist, well, then this sum does not exist. And we say the series diverges. Okay. All right, so let's look at an example of doing this process and see if it makes sense. And the example we're going to look at is if you look at the example 5.7 in your text. The author proposes to you to evaluate the limit of the sequence of partial sums for 3 particular series he wants you to look at. Okay, so let's take a look at the first of those. The infinite series that we're looking at in our first example is the sum of n over n plus 1. And so let's think about what the partial sum, s sub k, would look like. Again, that's the sum from 1 to k, the first k terms of this. And so that's going to look like when n is 1, 1 over 1 plus 1, or 1/2. When n is 2, 2 over 2 plus 1, or 2/3. When n is 3, 3 over 3 plus 1, or 3/4. And you start to see the pattern here, 4/5, 5/6, and so on, up to the kth term is where you stop, so that's k over k plus 1. And so what I can notice here is that the term 2/3 is certainly bigger than 1/2. So I can say, okay, the first term's 1/2. The second term, I know, is bigger than 1/2. So that means this sum here is going to be bigger than 1/2 plus 1/2 plus these. Same as 3/4 is bigger than 1/2. 4/5 is bigger than 1/2. 5/6 is bigger, than 1/2. All these terms, k over k plus 1, all bigger than 1/2. And that sum of 1/2, k times, is k times 1/2, or, of course, k over 2. So what I can see is this sum, while I can't figure it out exactly, I know that this sum is bigger than k over 2. I'm trying to determine whether the limit of this sum exists. The limit, as k goes to infinity, of that sum, meaning the limit, as k goes to infinity, of this from 1 to k of n over n plus 1. And what I can do now is I can compare it to the sum of this. Okay? I know that this sum is smaller than this. So I know that this limit of this sum is smaller than the limit, as k goes to infinity, of the sum k over 2. And this limit, as k goes to infinity, is simply infinity. And so what we've shown is that this limit, in fact, is infinite, does not exist, and therefore the series diverges. Okay? All right, so that's our first example. Our second example, the author asks us to look at the sum from 1 to infinity of -1 raised to the nth power. So of course, if you write out some of the terms, you get a good feel for this. When n is 1, that's -1 to the 1. When n is 2, that's -1 squared, which is 1. When n is 3, that's -1 cubed, which is -1. When n is 4, -1 to the 4th is +1. And so you get this pattern. Okay? All right, so what would the partial sum look like? Well, let's write down the first sums. S sub 1, the first sum, that's just the first term, -1. S sub 2 would be the sum of the first 2 terms. -1 plus 1 is 0. S sub 3, the sum of the first 3 terms. -1 plus 1 plus -1 is -1. S sub 4, the sum of the first 4 terms. -1 plus 1 plus -1 plus 1 is 0. And you start to see this alternating pattern. Of course, S5, well, that's just the first 4 terms plus the 5th, so 0 plus a -1. S6 is S5 plus a 1, so that's 0. And it goes back and forth and back and forth. So while you could write down, if you wanted, the partial sum this way, S sub k, it's either equal to -1 or 0. It's equal to -1 when the subscript is odd. It's equal to 0 when the subscript is even. Think about what the limit of that would be. This bounces back and forth between -1 and 0, back and forth forever, -1, 0, -1, 0, as k travels on. So this does not converge down to a limit value. this does not exist. And since the limit of the partial sum doesn't exist, we say the series diverges. All right, let's take a look at our third example in this. Example 5.7 the author puts forth. Okay, we're looking at, get to your center there, in part C, the sum, as n goes from 1 to infinity, of 1 over n times n plus 1. Now, the interesting thing about this is we can do a partial fraction decomposition on 1 over n times n plus 1, and we can write it as 1 over n minus 1 over n plus 1. In other words, if you add those two fractions together, you just get 1 over n times n plus 1. Okay? Think about it like a half minus a third. A half minus a third is 1/6, which is 1 over 2 times 3. So that's the decomposition of this. Now, how does that play out? Well, when we write s sub k, okay, the sum of the first k terms, well, when n is 1, you get 1 over 1 minus 1 over 1 plus 1. When n is 2, you get 1 over 2 minus 1 over 2 plus 1. When n is 3, you get 1 over 3 minus 1 over 3 plus 1. And this goes on till you get to k, where you have 1 over k minus 1 over k plus 1. Now, when we look at this sum, what we notice is the following. You have a negative a half here plus a half. Those cancel each other. You've got a negative a third plus a third. Those are going to cancel each other. The negative a fourth, well, that's going to cancel with the first term of the next pair. And this pattern goes on, right? Second of the previous cancels with the first of the following. Okay? Second of the previous cancels with the first of the following. So this first of this one is going to cancel with the second of the previous. And that means all you're going to be left with is this very last term and this very first term. The partial sum, in other words, is 1 over 1 minus 1 over k plus 1. Okay? Now, take the limit. Okay? This limit is done, again, to determine whether this series converges or to a value or diverges, meaning doesn't exist. And look at how easy it is to take the limit of this. As k gets infinitely large, this 1 doesn't change, but this k gets infinitely large, making this part be 0. So the series converges to 1. In other words, this adds up to 1, this infinite set of numbers. Okay? And so that's our tool for analyzing how we get the sum of an infinite set of numbers. All right, now there's one very, very special infinite series for us to be aware of. This is the most useful of the infinite series. And it's called the Harmonic Series. Okay? The harmonic series is defined by this. It's simply adding up 1 over n as n goes from 1 to infinity. In other words, when n is 1, you get 1 over 1. When n is 2, you get 1 over 2. When n is 3, you get 1 over 3. When n is 4, you get 1 over 4. And on and on. Very tedious. Going on and on and on forever. Okay? Now, what is clear is we can calculate partial sums for this thing to try to figure out what this does. Okay? And in fact, if you were to calculate just the first partial sum, s sub 1, it's just 1, the first term. S sub 2 is 1 plus a half, 3 halves, right? S sub 3, well, now you're adding these first three terms, right? 5, 6 plus 1, 11, 6, and you get the idea. Okay, the terms are growing, of course. You're adding more and more every time, so the terms are going to be getting bigger in the partial sum. They get bigger very, very slowly, however. In other words, I can tell you this. For the partial sum to be bigger than 1, for the partial sum S sub k to be bigger than 1, how many terms do we need? Number of terms? Well, that's easy. You just need 1 for it to be bigger than or equal to 1. For the partial sum to be bigger than or equal to 2, how many of these would you have to add up? Well, if you add up the first 4 terms, you'll be bigger than or equal to 2. For the partial sum to be bigger than or equal to 3, well, now you have to add up the first 11 terms of this series. For the partial sum to be bigger than or equal to 4, now you'd have to add up 31 terms. For the partial sum to be bigger than or equal to 5, you'd have to add up 83 terms. For the partial sum to be bigger than or equal to 6, you'd have to add up 227 terms. Partial sum to be bigger than or equal to 7, 616 terms. And I know this is a little bit tedious and boring to watch me do this, but try to get the point of what we're trying to get across to you here. When you're adding up these terms, these values that you add up after a while, they're so tiny that it takes so many of them to account to much that you end up having to get a huge number of terms just to get a small partial sum. I have to impress this upon you a little further. To get the sum of all these terms to be greater than or equal to 8, you'd need 1,674 terms. For 9, you'd need 4,550 terms. Okay. To get 10 as your sum, you would need 12,367 terms. Okay. What about to get 100? Okay. Well, then you would need the number of terms to add to get this sum to be bigger than or equal to 100. You would need 1.509 times 10, and I have to use exponential notation because the number is too large for me to actually write, where the power is 43. In other words, 1 followed by 43 decimal places. That's a huge number of terms. Okay, so huge that it's astronomical. Okay. All right, so the point we're trying to get across to you is the sum, and you've only gotten the sum to 100, and you've added up that many terms. We don't even have a name for that many zeros on a number. Okay, but to add up that many terms to get just 100 means this is growing very, very slowly. And yet, even though it's growing very slowly, it still is the fact that this sum is infinite. And this is how we can show you that. Okay? I want to show you that the sum is infinite. Well, do the first partial sum. Its first term is just 1. Okay? That second partial sum, remember that's 1 plus a half. So that is 1 plus 1 times a half. Okay, that third partial sum, we can think of that as 1 plus 1 times a half plus 1 times a third plus 1 times a fourth. But a third plus a fourth is bigger than a half. So I could say the following. Okay, that third partial sum is bounded below by 2 times a half. In other words, you got the half from here, and then you have a third and a fourth, which add together to be bigger than a half, so that means that you have another half at the very least. S sub 4, 1 plus 3. Oops. S sub 1 is 1. S sub 2 is 1 times a half. This is S sub 4, the first 4 terms. S sub 8, the first 8 terms. going to be 1 times 3 times a half. Now, again, this goes back to the idea that the partial sum of 1 over n is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, and on, right? And what we're saying here is s sub 1 is this, s sub 2 is the sum of the first two, s sub 4 is the sum of the first four, where you take these two and you say, you know what? These two added together is bigger than a half, so 1 plus a half is smaller than that, s sub 4. S sub 8, you say, okay, these four. An eighth plus an eighth plus an eighth plus an eighth would be a half, so this is certainly bigger than a half. 1 plus a half plus a half plus a half is 1 times plus 3 times a half. So we're getting a formula here. S2 to the n power is bigger than or equal to 1 plus n times a half. And so now I can use that to take the limit as n goes to infinity of the partial sum and say that limit is bigger than this lower bound on it. And that n goes to infinity, that becomes infinity. And you've proven the harmonic series diverges. Okay? The harmonic series diverges, although it diverges extremely slowly, as these numeric values indicate for you. And this is not something you see commonly presented, but this is the idea. It's extremely slow. To get the sum to be bigger than 100, you need 43 decimal places on your n. Okay? Okay. Now, let's take a look at some of these algebraic properties of convergence series. This is theorem 5.7. So, algebraic properties of convergent series, okay? Assume you have a couple of convergent series. And assume you have a constant. Then, the two things you know. First, if you add these two series together, or subtract them, doesn't matter, term by term, that's going to be the sum of the first series plus or minus the sum of the second series. So that means this converges. Because after all, this is a value and this is a finite value. And the second thing you know is if you multiply a constant by the terms of your convergent series, then you could factor that constant out and multiply it by the sum of the convergent series. Okay. All right, now, the next thing we're going to do is look at a special type of series called a geometric series. And we look at this geometric series because it lends itself to us understanding the summation process very well, for one reason, and a second reason is it's also a very useful series. So another very useful series, the geometric series. And the geometric series is simply a discrete analog to the exponential function. So the geometric series looks like the following. You've got some constant a times r, a base raised to the n minus 1 power as n goes to 1 to infinity. So when n is 1, that power is 0, and you're just left with the a. When n is 2, the power up here is 2 minus 1 is 1. You have ar. When n is 3, the power is 3 minus 1 r squared. You have ar squared. And that's the pattern you get. Okay. So think about what the partial sum of this looks like. S sub k. That's from 1 to k of ar n minus 1. That's going to be a plus ar, so ar squared plus ar cubed plus all the way out to, you stop when n is k, so a times r to the k minus 1. Okay? Now think about how you would go about figuring out what that adds up to. Well, one little trick you can use. The fact that you have this thing just increasing by r every time lends itself to this following reasoning. Take that partial sum s sub k and multiply it by an r. That means all you're doing is multiplying all these terms by r. So that means a gets multiplied by an r, ar gets multiplied by another r, ar squared gets multiplied by another r, ar cubed gets multiplied by another r, and so on and so forth till ar to the k minus 1 gets multiplied by another r, increasing this power by 1 up to ar to the k. Now think about what happens if you were to subtract. Take the partial sum s sub k minus the partial sum s sub k when multiplied by r. In other words, all this minus all this. Well, here's an a, but here's an ar that's going to cancel with this ar when we do the subtraction. Here's an ar squared, which is going to cancel with this ar squared when you do the subtraction. This ar cubed is going to cancel with ar cubed as we do the subtraction, and so on and so forth. So the term here is going to cancel with the previous term in the sequence here, meaning this is going to cancel with whatever came next, this would cancel with whatever was before this, and the last thing you're left with is subtracting this ar to the k. Now our goal is to come up with a formula for that partial sum so that we can take the limit of it. We want to know what s sub k is as a formula. So let's factor s sub k out on the left. That's 1 minus r. And then divide both sides to get s sub k is a minus ar to the k over 1 minus r. There is our formula for the partial sum of the geometric series. Now take the limit. The limit as k goes to infinity of s sub k. That limit as k goes to infinity only affects this term right here. And what we know is this: if the value of r is small, raising it to higher and higher powers is going to make that term go to 0. Meaning if the absolute value of r is less than 1, when I take the limit, this term is going to go to 0. Okay, that term is going to go to 0. You'll be left with a minus 0 over 1 minus r. A over 1 minus r is your formula. Okay? Whereas if r is bigger than 1, then this limit doesn't exist. This is going to oscillate back and forth, getting larger and larger. And in fact, if r is equal to 1, well, if r is equal to 1, go back up here. R is equal to 1, you got a plus a plus a plus a plus a. You're adding the same term an infinite number of times. And that's going to diverge. If r is negative 1, then this pattern oscillates. A, negative a, negative a, negative a. And as in a previous example we saw with 1s and negative 1s, that's going to diverge because the limit doesn't exist. So that's how we sum a geometric series right there. We have our formula for the process, a over 1 minus r, if the absolute value of r is sufficiently small. Okay? Now, the next type of series we're going to look at is called a telescoping series. Okay? The telescoping series is simply a series in which most of the terms in the partial sum actually cancel each other out. And I want to look at several examples to see this at work. So let's take a look at, from your exercises, problem number 102. 102 in the book here, paging down. There we go. And the prompt says evaluate the following telescoping series or state whether the series diverges. So in 102, the series that we're given is the sum as n goes from 1 to infinity of 1 over n to the 13th power minus 1 over n plus 1 to the 13th power. Okay, so think about what the partial sum s sub k looks like. Okay, that means the sum of the first k terms. So that's 1 over 1 to the 13th minus 1 over 2 to the 13th. Then when n is 2, that's 1 over 2 to the 13th minus 1 over 3 to the 13th. When n is 3, that's going to be 1 over 3 to the 13th minus 1 over 4 to the 13th. And this pattern goes on and on until you get to k. 1 over k to the 13th minus 1 over k plus 1 to the 13th. Okay, so there's your partial sum. Now look to see that the terms in the middle actually cancel. The negative 1 over 2 to the 13th and the positive 1 over 2 to the 13th cancel. Negative 1 over 3 to the 13th and positive 1 over 3 to the 13th cancel. And by now you see the pattern, right? This will cancel with the next one. This cancels with the previous one from before it. So all you're left with is the very first term minus the very last term. In other words, s sub k is 1 minus 1 over k plus 1 to the 13th power. Now, once we've done that, then we can take the limit. And as k goes to infinity, of course, this 1 is unaffected. But here, as k goes to infinity, this denominator gets infinitely large, driving this term to 0. And so you're left with a sum of 1. This infinite series sums to a value of 1. It converges to 1. All right, let's take a look at number 104. In 104, you've got the sum, as n goes from 1 to infinity, of sine of n minus sine of n plus 1. So think about s sub k for that. When k is 1, okay, or if when the first term n is 1, you get sine of 1 minus sine of 1 plus 1, which is 2. When n is 2, that's sine of 2 minus sine of 3. When n is 3, that's sine of 3 minus sine of 4, and on, till the last term, sine of k minus sine of k plus 1. And now think about the cancellations you get in this telescoping series. Those cancel, this would cancel with this will cancel with the previous one to it. And so all you're left with again is the first term minus the last term. And so now you want to analyze this with the limit. The limit of the partial sum. And again, well, this one doesn't have a k this term, so the k doesn't affect it as it goes through the limit process. That's just the sine of 1. This has a k. This is affected by the k going to infinity. But this is a sine function, and sine function oscillates forever, meaning this does not have a limit. And so that does not exist. All right, let's take a look at 106. Express the following series as a telescoping sum, and then evaluate its nth partial sum. So 106. n equals 1 to infinity of 2n plus 1 over n squared plus n quantity squared. And the author gives you a little hint here. He says factor the denominator, meaning take out an n times n plus 1, all squared, and then use partial fractions on this thing. So, partial fractions, when applied to this rational function, allows us to rewrite it this way. 1 over n squared minus 1 over n plus 1 squared. Now, think about the partial sums for this. S sub k, the first k terms added up. When n is 1, you get 1 over 1 squared is 1, minus 1 over 2 squared. When n is 2, you get 1 over 2 squared minus 1 over 3 squared. When n is 3, 1 over 3 squared minus 1 over 4 squared. And on, the last one being 1 over k squared minus 1 over k plus 1 squared. And now see the cancellation pattern. These cancel, so that means this will cancel with the next term, this canceled with the previous term, and you're left with the very first and the very last again. Now you take the limit to see if this converges or diverges. As k goes to infinity, this term goes to 0. You're left with 1. The series adds up to 1. Okay. So let's now take a look at a couple of exercises in the book just to make sure we understand one last concept here, and then we'll be done. In these exercises, 97 through 100, the author has asked you to use an identity that he provides to you to rewrite some expressions. Okay. So, in 97 to 100, we use the identity 1 over 1 minus y is equal to the sum, as n goes from 0 to infinity, of y to the n. In other words, 1 over 1 minus y is equal to y to the 0, which is 1, plus y to the 1, plus y squared, plus y cubed, and on and on and on forever. Okay, and that's an identity we have. Okay, so let's take a look at problem number 97. You're given x over 1 plus x, and you're asked to rewrite it. Well, simply take the x in the numerator out, and the 1 plus x, write it as 1 minus negative x. And now you've got this 1 over 1 minus a term, just like the 1 over 1 minus y. Playing the role of y is the negative x. So now you have the x in front times this sum of, instead of y, it's negative x. And there's the summation. Okay, in 98, you have the square root of x over 1 minus x to the 3/2 power. So again, take the square root of x out from the top. So you have a 1 in the top, 1 minus x to the 3/2, and then simply say that this x to the 3/2 is playing the role of y here. So that's the square root of x times this sum, n equals 0 to infinity of, instead of y again, x to the 3/2 raised to the nth power. In 99, we had 1 over 1 plus sine squared x. Well, write that as 1 over 1 minus a negative sine squared x, and let that negative sine squared x play the role of the y. And there you got it. Of course, you can rewrite these things, right? You can take this -1 to the n out as a separate term. You can write this as sine to the 2n. So you can do fancy things like this, but it doesn't change your answer. So don't feel compelled to do things like this. It's the same answer. 100, our last one. Secant squared x. Okay? Well, secant squared x is 1 over cos squared x. And what I know about cos squared x is it's 1 minus sine squared x. Now I have it in this form here. We're playing the role of y as sine squared x. And I'm done with the problem. Okay? All right. So please go ahead and give those homework exercises a try. And as always, contact me if you have questions or concerns about anything so that we can discuss it. Thank you.